This video is going to talk about dummy variables. Dummy variables provide a way for us to include categorical variables in a regression. So let's start with the simplest case, which is when we have a categorical variable that only takes two values. One example of this comes from the quality control case that we looked at earlier. So in the quality control case, the AM variable took the value 1 whenever the shift was from the morning, and it was 0 whenever it was the afternoon shift. So if we go back and look at that data set, you'll see sure enough, AM takes only the values 0 and 1. These variables that take only two values are very common. So if you want to find out the effect of gender, well, gender usually takes two values, and we would create a similar dummy variable to understand its effect. So to understand what's going on with these dummy variables, let's fit a regression of defect rate on AM, the dummy variable. We're going to interpret that and then compare what we get if we were to run a t-test. So regressing defects on AM gives us this model. So what is the estimated regression equation? Well, it's 16.92 plus 20.44 times AM. So let's just think about this. If we have an afternoon shift, what is the value of AM? Well, it's 0, and we don't need to add 20.44. So the intercept in this case gives us the defect rate for an afternoon shift. Now, if it's a morning shift, we're going to take the intercept and add to it the value 20.44. So the sum of those two values, which is about 37, is the defect rate, the mean defect rate for the morning shift. What does this 20.44 tell us? It therefore tells us the difference between the morning and the afternoon shift. So this p-value is really evaluating whether or not the two shifts have the same defect rate. If they have the same defect rate, then this coefficient would exactly be 0. The fact that we're rejecting it is an indication that the defect rates are not equal, at least on the surface. Remember, after we controlled for rate, they were equal, but let's just consider this example without controlling for rate. Now, let's compare this with what we would get from an independent sample t-test where we assume equal variances. So here's how I run such a t-test. Let's start out with the last line in this output. The last line in the output gives us the mean for group 0, 16.92. Now that number 16.92 is the mean for the afternoon shift. That should look very familiar. And so if we go look upstairs, that's exactly what we got for the intercept. So that is the mean for the afternoon shift, as I indicated earlier. Now what is the mean for the morning group? Well, it's 37.36, and we can compute that by adding these two numbers. So 16.92 plus 20.44 gives us that. Now let's go look at the output. So the output says the p-value to test the equality of those two means is 0.002295. Well, that number is exactly equal to the p-value for AM. So AM is telling you the difference. This is the p-value for the difference. You're going to note that the t-statistic is also equal, 3.355, 3.3547, which rounds to 3.355. The t-test is computing the difference in the different direction, and that's why you get the negative sign. So the point here is that we can use a dummy variable in a regression, or we can use a t-test and we'll get exactly the same result. And so testing whether beta equal to 0 in the case of a simple linear regression is entirely equivalent to testing the equality of these two means with an independent sample t-test. What happens if you have more than two levels? So if you have more than two levels, like we had with the click ballpoint pens example, it's going to get a little bit more complicated. So in general, If your categorical variable takes k levels, you're going to need k minus 1 dummies. So in the case where it took two values, AM or PM, we need 2 minus 1 or 1 dummy. So we need a dummy either for AM or we would need a dummy for PM. And in either case, we would get the same conclusion. Now, if we wanted to include the wholesaler efficiency variable as a categorical variable, this variable happens to take 4 values, and we're going to need 4 minus 1, or 3 different dummies. So if we go look at that data set, click, and let's just look at the first 10 observations, you're going to see that I've already hard-coded 3 dummies, fair, good, and outstanding, and this will do the trick for us. So we could regress sales on, let's include ads, reps, and then I'm going to include three of these dummies. So fair plus good plus outstanding. And if I do a summary on fit, we see the results. So the results are, we get an estimate for fair. Now let's just think about what fair is. So fair is a dummy that's going to take the value 1 whenever the wholesaler variable was fair, 0 otherwise. Good takes the value 1 if the wholesaler is good, 0 otherwise, and outstanding takes the value 1 if it's outstanding, 0 otherwise. And so we'll see exactly that. If we have a wholesaler who is 4 or outstanding, notice that outstanding is 1, the other 2 are 0. If the wholesaler is only a level 2, so 2 is fair, fair gets set to 1, the others are 0. What happens in the case of a poor wholesaler, like in case 5? Well, what you'll see is that all 3 of the dummies are 0. Let's try to interpret the regression coefficients now. So fair tells us the difference between a poor and a fair wholesaler on the average. So fair wholesalers are 9 better than poor wholesalers. Good wholesalers are about 20 better than poor wholesalers, and outstanding wholesalers are about 33 better than poor wholesalers. Now we could also say that a fair wholesaler is about 11 worse than a good one. So if we take 20.28 minus 9.24, you get about 11. So the difference between fair and good is about 11. The difference between good and outstanding is about 13. We could use a different set of dummies if we want. So I'm going to make a new dummy variable. So let's have a new variable, click $poor. And click $poor is going to equal 1 if click $efficiency is equal to 1. Now I'm going to cast this as a numeric variable. So as.numeric. And if we look at our first couple observations again of click, what you're going to see is that now for this observation 5 where the wholesaler was a 1, poor is equal to 1, and the other observations are 0. I'm going to fit a different model. So fit 2 is equal to an LM of sales on ad plus reps. And now let's omit outstanding. So it'll be poor plus fair plus good, and we'll omit outstanding. Remember I said you need 3 dummies if you have 4 levels? And now we get a different set of dummies, although they look similar. So let's interpret the coefficient for poor. So poor says a wholesaler that's poor is 33 worse than one that is the base category, outstanding. Let's interpret the category for good. So let's call this about minus 13. So good wholesalers are about 13 worse than outstanding supervisors. And note that that was what we concluded up here. So there was a difference of about 13 between good and outstanding. So my point here is it doesn't really matter which category we choose to omit, we'll get the same answer maybe with after doing a little bit of arithmetic. So we get minus 13 here, whereas upstairs we had to subtract 20.23 from 33. Now, we've created dummies. So we have these dummies. This is really the hard way to do it. There's a much easier way in R and most statistical software packages, and that is to include this as a factor level variable. So I'm going to have a new fit. Let's call it fit 3. And this time I'm going to regress sales on add plus reps, plus I can cast the wholesaler efficiency variable as a categorical variable. So if I just say as factor efficiency, this tells R that efficiency is a factor variable. In other words, make it dummies. If I do a summary on fit 3, what you're going to see is that now R has chosen a base category, and they chose it to be the first one, poor, and included dummies for the other levels. And you'll note that this is exactly the same as what we had before. So if we look upstairs, it was 9, 20, and 33. Down here we have 9, 20, and 33. So we get exactly the same result. One benefit of doing the regression this way is that we can use drop 1. So I use drop 1 on fit 3, and let's do an F test on it. R is going to test whether any of the 3 variables are significant. So ads, if we drop ads, we lose 41,000. If we drop reps, we lose about 55,000, 54,000. Now, if we drop wholesaler efficiency with 3 different dummies, so in other words, if we dropped all 3 of those dummies, the F, we lose about 44.57 in explaining. Now, this p-value is telling us that those 3 dummies are not significant. We don't need them. Now, we could have done this with the general linear hypothesis test. So I'll show you briefly how we could do this. Let's fit the reduced model. Let's call this fit 4. And so this will be sales on add plus reps, and our data set is click. Now I'm going to take the deviance of fit 4, and so this is the amount unexplained by that model. The deviance of fit 3, this is that full model that we just estimated, is 71,000. So let's take the difference between those 2 deviances. So deviance of fit 3. And notice that this is saying the difference in the explaining that we do is about 44.57 if you round that. And that's exactly what drop 1 did. So what drop 1 is doing is computing the difference between those deviances. Now, where does this p-value come from in the F statistic? Well, that just comes from that general linear hypothesis test that we did a while back. We have to go flip back here and I'll show you exactly where that was. So here's that general linear hypothesis test that R is doing to do that drop 1. So I'll refresh your memory on on what R does. It says take the difference in the deviances and divide by the number of degrees of freedom. So we have 3 degrees of freedom. Now we need to, so that's that difference. And if I take, let's do an ANOVA on fit 3 on the full model, you're going to see that the mean squared error is 2089. So if I divide this thing by 2089, I get my F statistic, which is 0.7111, and you'll see that's exactly what shows up there. So that's where the F statistic comes from. Where does that p-value come from? Well, the p-value comes from taking 1 minus PF, the probability of an F distribution. What are the degrees of freedom? Well, I have 3 degrees of freedom for the numerator, and I have, you're going to see 34 degrees of freedom right here for the denominator. So let's just type that in. And what you'll see is that it's 0.552, and that's what we got up here, so 0.552. Again, this is not significant. So maybe I'll summarize the key points. If you want to include a categorical variable, use dummies. You need one less dummy than the number of values that variable takes. And then you can use this drop one to determine, what is the effect of including all those dummies. And it's just saying it's not helping us very much. So we could drop the wholesaler efficiency variable in this